An alien world of landscapes you never dreamed existed. Vast mountain ranges, unending plains, violent volcanoes. But this is no alien planet. It's our own world. These are landscapes of the ocean floor, normally covered by miles of water. But all around the globe, scientists are mapping the seabed, collecting data and building up a picture of the terrain below the surface. We've combined the very latest scientific data with specially developed computer animation software to create the landscapes of the ocean floor. Now we'll pull an imaginary plug and drain all the water from the ocean. With no water, the planet looks completely different. This is the world we're going to reveal. The ocean, often wild and hostile, difficult and dangerous to explore. Yet water covers more than 3/4 of the globe, hiding most of planet Earth from view. Light only penetrates a few hundred feet below the surface. Beyond that, the ocean depths are pitch black. Explorers who venture into its depths are limited to what their lights reveal. But the view is captivating. This mysterious world plunges as deep as 7 miles beneath the waves with spectacular landscapes that dwarf anything on dry land. Only 1% of the seafloor has actually been explored, making it the final frontier in our quest for knowledge about the evolution of our planet. New technology gives us the tools to expose this vast unseen territory. We will lower the sea level a step at a time and stop at each stage to study the newly exposed ocean floor. Exploring exotic undersea locations like the Hawaiian Islands of the Pacific, the stunning depths of the Caribbean, and the majestic mountains of the mid-Atlantic. Draining away the water, going deeper and deeper to the deepest spot on the planet. The first stage begins at the coastline, zooming into Monterey Bay, California. There's a spectacular landscape just beyond the surf and the forests of kelp. Its shape emerges as soon as the water disappears. What's revealed is a massive canyon, nearly 300 miles long and up to a mile deep. Although scientists have only recently mapped Monterey in detail, it's now one of the best-known landscapes of the ocean. On its shoreline is the Monterey Bay Aquarium Research Institute. Here, scientist Charlie Paul is gradually making a detailed image of the Monterey Canyon using the latest technology.
In the last couple of years, we've been using an autonomous underwater vehicle and that allows us to fly from the head of the canyon right down through the canyon, and we're able to make maps of the canyon floor.
The AUV is programmed to fly a given route through the canyon, and it's packed with advanced sonar equipment. Sonar uses pulses of sound, and, unlike light, sound travels huge distances through water. This reveals the shape of the canyon in detail. Mapping Monterey Canyon is relatively easy. It lies just a few hundred yards from the coast, making it accessible to scientists. Mapping the rest of the ocean floor is much more difficult. Scientists put sonar on ships to survey areas of ocean floor that are larger and farther from shore. It sends out broad sweeps of sound powerful enough to reach the deepest parts of the ocean. The sonar transmits pulses of sound, and the time they take to bounce back is measured very accurately.
We're ready.
This tells the computer how far away the ocean bottom is, and as the ship moves forward, it gradually builds up a detailed picture of the sea floor.
Every ping is giving us an individual depth. So each of these pixels here that we're seeing here are individual depths. Really showing us what the seabed is doing. We will turn, come round, and then go up here, start collecting data coming up here. Just turn when you want to. So here we are, starting to turn. So we got full 100% coverage of the sea floor.
The ship tracks back and forth in a pattern the scientists call mowing the lawn, until a full picture of this patch of seafloor has been made. Mowing the lawn takes time, and only small patches of ocean floor have been mapped in detail. But maps of Earth's ocean floor are beginning to take shape, and information is building up to give a more complete picture of the landscapes hidden by the water. Scientists feed sonar data into a system called Fledermaus, a computer program that models the ocean floor in 3D, using color to represent different depths. Fledermaus shows us the peaks and the valleys with precision. For a more realistic experience, we turn to computer animation. Ocean topography data is run through customized software, and suddenly, the remote ocean floor comes to life. These vivid images add a whole new dimension to undersea research. Oceanographers can virtually walk on the deepest, flattest plain, or stand among black smokers spewing hot water and minerals. Many of the landscapes have parallels on dry land, places that compare to the twins underwater, like Monterey Canyon. It's almost the same size as Arizona's Grand Canyon. And they both run about a mile, or 5,200 feet from rim to bottom. There is one big difference. The Grand Canyon was carved by the Colorado River as it cut through layer upon layer of rock. There is no river at the bottom of the Monterey Canyon. So, how was it created? Scientists search for the answer. The floor of Monterey Canyon lies beneath 10,000 feet of water in some places, making it difficult to answer the most basic questions about how it was formed. To study the bottom of the canyon and collect samples of sediment, scientists dispatch remote-controlled vehicles, or ROVs, to reach the canyon floor 2 miles below. Conditions are harsh at these depths, with crushing pressure that's 300 times greater than at the surface. Every task is a challenge.
When you do this with an ROV, it is essentially a neutrally buoyant device. So if you go sit on the floor of the canyon and start to just push in cores, what you do is just push the ROV up. So to get around this, we started using a device which is a vibrocore, which we mounted on the front of the ROV.
Inside its shell, this device vibrates and sinks into the seabed under the weight of its heavy metal frame, allowing the ROV to extract core samples. These cores show that the canyon floor is made of a jumbled mixture of sand and pebbles, which must have been created by a major disturbance. Charlie thinks that an avalanche periodically blasts through the canyon, and perhaps such events in the past helped carve this huge structure. So much material rips down the canyon that it can even be seen on sonar surveys. A huge fan of debris is building up at the mouth of the canyon, shown in purple on this Fledermaus model. This material comes from the shore of Monterey Bay itself. Waves carry sand and gravel toward the center of the bay, where the head of the canyon lies. And when enough builds up, it triggers a submarine flow down the base of the canyon. These events happen so fast that it's hard for Charlie's team to get the data they need. So they set up new methods to monitor the canyon. First, surface buoys are connected by fiber optic cables to instruments deep in the canyon. Solar panels and windmills generate power, feeding it down to the instruments and then transmit data from the deep sea by satellite to shore. Eventually, engineers run power and data cables from the shore to a permanent science station on the ocean floor. This allows scientists to plug in their experiments and run them 24 hours a day, 7 days a week.
We're providing 10,000 watts of power out to 8 science ports, 31 miles west of here, in 3,000 feet of water.
This science station will soon be operational, helping scientists to understand more about how the canyon works. The bonus is that it also gives scientists a new way to understand the odd creatures that live at these depths. Down here, they have never known the sun and lived their entire lives in the inky blackness. Yet some of these animals have turned the darkness to their advantage. They make their own light by a process called bioluminescence. Edie Witter has spent many years studying bioluminescence, in the lab and in the deep ocean.
Bioluminescence is something you really got to see to believe. It changed the course of my career. My first dive in a deep diving suit was down to 880 feet, and I turned out the lights and just couldn't believe the amount of luminescence that I saw. It's the greatest light show on the planet. You just can't believe this miraculous fireworks display that's happening right in front of you. And so I developed this technique where I put a screen out in front of the submersible, and then I had an intensified camera inside the sub with me focused on that screen, and then if I moved the submersible forward, critters bumping into the screen would be stimulated to luminesce.
Different creatures put on these dazzling light shows for different reasons.
If you've ever tried to find food in the dark, you know that having a flashlight's a pretty handy thing. So some of the animals have built-in flashlights. Some of them use luminescent lures to attract prey to them. Some of them use it to attract a mate, just the way fireflies do on land.
But some creatures use light displays for a more intriguing reason, one that Edie calls the burglar alarm.
One of the ways animals use their luminescence to defend against predators is to attract the attention of a larger predator, because that larger predator may hopefully attack what's attacking them, and in the scuffle they'll have a chance for escape. So, you know, some mushy little jellyfish can put on this enormous light show that can be seen from 100 meters away, and some big predator will come in. Well, it doesn't want to eat the jellyfish, but it might want to eat whatever's munching on the jellyfish.
The burglar alarm system attracts predators, which gave Edie an idea for a different way to study deep-sea life.
We developed this electronic jellyfish that imitates the burglar alarm display of certain bioluminescent jellyfish, and it was successful beyond my wildest dreams.
The rig was taken down to the seabed by a submersible and then left in the darkness, where a special low-light camera could observe creatures without them being blinded by the sub's bright lights. Even before the sub returned to the surface, the bait was drawing in scavengers.
All right, buddy. We're backing up. Don't worry about it.
And then I activated the electronic jellyfish for the first time with this burglar alarm display, this pinwheel of light swirling around. 86 seconds after I turned on that pinwheel display, we recorded a squid over 6 feet long that is so new to science that it cannot be placed in any known scientific family. That's great! That's it. This opportunity to actually put it on the site that's going into the Monterey Canyon is fantastic, because it's basically a plug in the bottom of the ocean. You get to plug in your equipment, and we just have the leisure to do the kind of science in the deep sea that is usually taken for granted on land.
Monterey Canyon, with its startling landscapes and creatures, is just a tiny glimpse into what we'll find on our journey to the deep. On a quest to know more about our planet, we're going to lower the water again, and this time move away from the coast and into the center of an ocean basin. Another area that is mapped in detail lies in the middle of the Pacific, the island chain of Hawaii. At the eastern end of the chain lies the Big Island, where Mauna Loa, the world's biggest volcano, rises 13,500 feet above sea level. Why is the Big Island so big? One theory is that it sits over a hot spot, a place where hot, buoyant magma rises toward the surface from deep within the earth. As the magma punches through the surface, it creates the island. Even today, the Big Island is very active. Another volcano on the flanks of Mauna Loa, called Kilauea, has been erupting for the last 25 years. Above the waves, the Big Island is impressive. But when we lower the sea level, its true size is revealed. The Big Island itself is big, but without the water, the island above the surface is dwarfed by the vast underwater cliffs. Measured from its base, this is the biggest mountain on Earth, rising 4,000 feet higher than Mount Everest. Looking down at the Big Island, as it's never been seen before, the ridges of its massive volcanoes are lost next to the rest of the mountain, normally hidden by the ocean. But we're not just visiting the Big Island because of its size. The Hawaiian Islands and the surrounding seafloor have been mapped so accurately that John Smith from the Hawaii Undersea Research Lab can use his computer to fly around the islands, above and below the water. And these surveys reveal a small underwater volcano, a seamount.
Here we have Loihi Seamount. It's an active volcano off of the Big Island of Hawaii. It's about 20 miles or so off of the southeast side of the Big Island.
The Loihi volcano lies 3,000 feet below the surface, but it's just as active as the volcanoes above the water. Magma below the seabed creates shimmering columns of hot water. Scientists have monitored Loihi since it was discovered in 1955, and they found that it's slowly growing toward the surface. It seems Loihi is being created by the same hotspot that gave birth to the Big Island. The Big Island is drifting off the hotspot, and Loihi may eventually take its place, growing larger until it breaks the surface as the newest Hawaiian island. Loihi shows us how the whole Hawaiian chain was created. Each island was born over the hotspot and, over millions of years, appears to have moved away to the west. But it's not the individual islands that are moving, it's the whole sea floor. All ocean floors behave like this, slowly creeping over the face of the globe. Loihi isn't the only discovery in these underwater landscapes. While witnessing the birth of a new island, scientists like Chris Kelly use the latest technology to find out more about what lives down here.
These are the Pisces submersibles. Usually we don't go below about 1,800 meters. Yeah, that's over 1 mile down. So it's pretty deep.
Glimpses of the abundant sea life in the tiny beam of light from the sub are simply stunning.
Being in the submersible and seeing these areas with your own eyes is an amazing experience. It's basically an alien world down there. Once you're below 1,000 meters, you see sponges that look like giant lollipops.
That's great.
Look at that, beautiful.
Some creatures, like this chimera, seem to be attracted to the sub. This is life in the slow lane. Goosefish sit propped on leg-like fins, patiently waiting for prey to pass within reach. A vampire squid, named for the webbing between its tentacles that looked like Dracula's cloak. And a creature named the Dumbo octopus, from its fins shaped like elephant ears that it uses to fly through the water.
One of the big thrills is that when you're going along in the submersible, you have no idea what's going to be over the next rise. It could be a brand new animal that no one has ever seen before. And that of course, is a tremendous thrill.
Scientists got a big surprise when they found large areas covered in coral. Until this discovery, it was thought that corals only lived in shallow tropical waters. Now it seems that corals live everywhere, even in the cold, dark waters of the deep. Shallow water corals depend on algae in their cells that use sunlight to make food, so they can't grow below depths of a few dozen feet. But when corals live all the way down here in the deep sea, how do they feed? Unlike their shallow water cousins, these corals don't need sunlight to grow, and they catch all of their own food. They cover large areas of the seabed in bright colors that are only seen when lit by the sub's light. These deep water corals hold another big surprise for scientists. Many grow to incredible heights that surpass most skyscrapers. In 2003, Frank Parrish and his team were studying Hawaiian monk seals in the deep sea when they found something completely new.
We had put instruments on seals to just study seals and then found that they were focusing all of their diving in one area, down to 300 to 500 meters, and we couldn't possibly imagine what it was that was so interesting at that site that the seals would be spending their time. When we got down there, it blew our minds. Right there, in that location, we had a patch of really, really lush, precious coral. So for some reason, the seals were very attracted to this site, and we wouldn't have found it had they not been out there showing us where it was.
But this raised another question. Why were the seals diving so deep?
The seals were going back to this site over and over again for some reason, and it's not clear what that reason is. We think they're probably feeding on the fish that are down there, but we haven't really been able to show that there are more fish associated with corals, so we're looking into that now.
It was a big surprise to find corals growing so deep, and an even bigger surprise to find places where they dominate the sea floor.
Deepwater corals are distributed throughout the world in all the oceans. The depth range goes all the way down to 4,000, 5,000 meters, all the way down to the seafloor. Basically, wherever there's cold water, you can usually find deepwater corals.
The more we look, the more we find. Deepwater corals are all over the globe. In some places, there is so much coral, it creates the landscapes of the ocean floor. But to see these landscapes requires very precise sonar surveys. One place that's been mapped in such detail is the deep water channel of Florida, the Straits of Florida, an area normally covered by around 2,000 feet of water.
The last 20-30 years, with the better exploration of the seafloor, we find them basically everywhere. And probably today we have more deep water corals on the Earth than we have shallow water corals.
Gregor Eberle and his team at the University of Miami have made detailed surveys of deep water reefs and find that they can grow into huge structures. Deep water coral mounds are scattered all along the Florida Channel, reaching incredible heights of up to 500 feet. These sonar surveys are so accurate that individual mounds can be recognized by their shape. So Gregor and his team have given them names.
We had mounds that looked like a heart, and we called them the Corazon Mound. Then we had mounds that were just grown together where it had two peaks. We called them the Twin Peaks. And the largest peak, and the most beautiful peak, I think, was the Matterhorn, this 120-meter peak on one of these ridges on the foot of Great Bahama Bank.
These Fledermaus models show the strange features that lie under the blue waters off Florida's coast. We get a sense of scale of these coral structures by comparing them to something more familiar, the famous skyline of Miami.
Behind it we have the Miami Brickell Avenue skyline, with the tallest building there, 240 meters high. That's the tallest residential area south of New York. The largest mounds in the deep sea are about that size that we know today. In the Straits of Florida, the mounds are a little bit smaller, a bit like the skyline in front of that tall building when it comes up to about 120 meters high and it goes down on the other side.
It's strange to think that hidden in the waters just offshore are structures made of coral as big as these buildings. So far, the features exposed by draining the ocean have been relatively small. But now we turn to the really big landscapes. And to see them requires a different way to analyze the deep that doesn't use sonar. This might come as a surprise, but the surface of the ocean isn't flat. It's covered in small hills and valleys that mirror the landscapes on the ocean floor. Some features are so big, they push up the water above them. A 3,000-foot mountain on the seabed only creates a hill of about 3 feet on the ocean surface. But we have satellites in orbit that measure height differences to around ½ an inch. So these satellite measurements help create a global map of the ocean floor. They aren't in as much detail as the sonar maps we've seen so far, but they do show us the major features of the ocean's landscape. One of the most obvious features on these maps is a long line of mountains running along the center of the ocean basins. This is the mid-ocean ridge, a vast chain of mountains, 40,000 miles long and hundreds, sometimes thousands of miles wide. It runs all the way around the globe, like the seams on a baseball. The Earth's crust is broken into slabs, tectonic plates, like the plates on a turtle's back. The mid-ocean ridges mark the edges of these plates. The next stage of our journey follows this mountain chain all the way around the planet. This mountain range is normally hidden under 2 miles of water. But there are a few places where the ridge appears above the surface, making it easier for scientists to study. Places like Iceland, Iceland is a harsh, rugged land, but its spectacular scenery helps scientists understand how the massive landscapes of the deep ocean were formed. On Iceland, 200 miles of the mid-Atlantic ridge are exposed. And here, the North American and European plates meet, a junction marked by a wide rift valley. The two plates are moving apart, creating deep fissures in the valley floor. But these are not the only signs of major geological activity. In places, there are pools of boiling water and spectacular geysers. This activity is driven by molten magma, not far below the surface. All of this scenery should really be hidden under 10,000 feet of water. So why is the mid-Atlantic ridge high and dry here in Iceland? Iceland is part of the vast mid-ocean ridge system that runs underwater all the way around the globe, but which rises above the surface here. One reason for this might be that Iceland sits over a hotspot, a rising plume of magma from deep within the earth, pushing the island up in the same way that the Hawaiian Islands were created. Iceland provides a unique glimpse of a landscape normally hidden by the ocean. Here, we really can walk on the ocean floor. But to walk on the most spectacular parts of the mid-Atlantic ridge, we need to drain more water from the ocean. We've lowered the Atlantic sea level by 15,000 feet, exposing the peaks of the world's longest mountain chain. Compared to Iceland, these landscapes are massive. The mountain chain here is hundreds of miles wide, and at its crest is a huge rift valley. In places, this valley is as deep as the Grand Canyon, but twice as wide. And a long line of volcanoes runs down the center. Just as in Iceland, the two sides of the rift valley are moving apart. And as they do, lava erupts from the volcanoes and then solidifies to form the new seafloor. This is where new seafloor is born. And slowly, this new seabed moves away to either side of the volcanoes as the rift valley spreads. So the ocean floor is continually creeping across the planet, spreading from the mid-ocean ridges. In the Atlantic, that movement isn't very fast, about an inch a year. So the volcanoes have time to build up the rugged terrain. The mid-ocean ridge doesn't run in a smooth line. In some places, it takes a sharp step sideways, often over hundreds of miles, along structures called transform faults. Here, the two plates are not pulling apart, but sliding past each other. There are places on land where two plates slide past each other like this. The most famous is in California. This small town straddles one of the faults so we can see its effects.
We're in Hollister, California, and we're standing on the Calaveras Fault. The Calaveras is one of the major faults of the San Andreas transform plate boundary. And where we are right now, the Calaveras Fault behaves in a certain way. It's called creeping. It's a creeping fault. Faults work in different ways. Some of them are stuck together and then move suddenly. And when they do that, they produce large earthquakes. Other faults, like the Calaveras, move slowly and chatter all the time. And you can actually see the effects of that slow movement on the streets of Hollister.
We can trace this fault across the town by the way the curbstones and walls are offset or cracked. This is geology in action, but it hasn't created any spectacular landscapes. Several of these faults run through California, the most famous being the San Andreas, the fault that devastated San Francisco in 1906. But even that fault isn't obvious.
If you were simply driving past here and you looked off to your right or left, you'd just see a flat field. You would have no idea that the San Andreas Fault was right here. If it wasn't for the fact that this fence was constructed after the 1906 earthquake and the fault continued to creep, but if you look out along the fence, you can see how it's bowed out to the right. And this bowing is a result of continuous creep or movement along the fault.
In some places, the San Andreas Fault has more of an impact on California's topography. It crosses the vast, empty Carrizo Plain, where this dried creek bed has been offset. The creek was straight, but now takes a right-angle bend for 100 yards, then resumes its original course. A giant version of the walls and curbs in Hollister. And on the Carrizo Plain, the two plates are not only sliding past each other, they're pushing together, raising a long line of low, rounded hills. But beneath the waves, transform faults produce scenery that has no comparison on land. So far, we've drained enough water from the ocean to reveal a giant canyon the size of the Grand Canyon just off Monterey Bay. Exposed the world's largest mountain. And the crest of an enormous mountain range that runs all around the globe along the center of the ocean basins. There's much further to go. The next stage explores the most extensive landscape in the world and the deepest part of the planet. To get there, we must travel further along the mid-ocean mountain range running down the center of the Atlantic. The line of the Great Mid-Atlantic Ridge sometimes takes a giant sideways step, a transform fault, and the most spectacular section is called the Romanche Fracture Zone. It's so big, with the water drained away, we can only appreciate its scale from an airplane. The fault valley is 200 miles long, 20 miles wide, and 4 miles deep. 4 times the depth of the Grand Canyon. The Romanche Valley is so deep that even with the sea level lowered by 15,000 feet, there's still water in the bottom. There's nothing on dry land to compare with this. As we continue draining the water along the mid-ocean ridge, the mountain range changes. The next part of the journey takes us into the Pacific Ocean, to a part of the mid-ocean ridge called the East Pacific Rise. It doesn't stand out on the globe like the Mid-Atlantic Ridge. This range is so wide and the slope is so shallow that driving across it is like driving across somewhere as flat as Kansas. If the mid-ocean ridge is so rugged in the Atlantic, why is it so flat in the Pacific? Because the East Pacific Rise is spreading much faster than the Atlantic Ridge, up to 6 inches a year. There's not enough time for big peaks to form before they move away from the volcanic activity. Even so, there's still some very dramatic scenery on this range. These sites are so deep that very few submersibles can reach them. This is Alvin from the Woods Hole Oceanographic Institution. It can dive as deep as 15,000 feet. And in 1977, descending on the mid-ocean ridge in the Pacific, it made an astounding discovery. Scattered along the ridge of the East Pacific Rise are deep-sea hot springs, hydrothermal vents. Scientists had no idea they existed until a few decades ago. Tall chimneys gush out very hot water, black with minerals, which gives them their name, black smokers. These are difficult, dangerous, and expensive places to visit. And, however advanced the technology, we can still only glimpse this landscape as far as the sub's lights penetrate. In a few places, there is enough data to build a hot vent site in 3 dimensions. At Lamont Doherty Earth Observatory, Vicky Farini has compiled some of the most accurate measurements of any vent site.
This is a 3D view of one of the vent fields that we mapped, and what we can see is fissures that come through the seafloor.
The bumpy texture is created by mounds of lava, and individual chimneys can be seen growing between 2 deep volcanic fissures.
This is probably the best kind of view that we can get with the technological limitations that we face.
Mapping such deep, remote places is an impressive achievement. But there are more accessible places on land that help us understand how these structures formed. Like Yellowstone National Park. Yellowstone is in the middle of the North American continent, but like the mid-ocean ridges, hot magma lies just below the surface. In Yellowstone, this magma creates pools and geysers that erupt with boiling water. Minerals dissolved in the hot water are deposited around the base of the geyser, slowly building up cones in the same way the vents build their chimneys. On land, wind and rain erode these cones so they don't grow very big. But underwater, with no erosion, the hot springs can build much taller chimneys that reach as high as a 20-story building. And on the mid-Atlantic ridge, deep-sea vents have built even bigger structures. This is the Tag Mound, and a 3D Fledermaus model shows that it is about 3 miles across. Using this data, we take away the 10,000 feet of water from above the Tag Mound. The hot water plumbing creates structures that could never exist above the waves. Deep underwater, on the mid-Atlantic ridge, the Tag Mound shows how these bizarre structures are built by black smokers. With computer animation, geologist Crispin Little walks among the chimneys to examine their hot water plumbing.
I'm standing on top of the Tag Mound here, surrounded by these fantastic black smoker chimneys which are gushing out this high temperature, up to 400 degrees centigrade hydrothermal fluid.
These underwater vents are powered by seawater that sinks down into the Earth's crust through cracks in the rock and is heated by magma just below the surface.
And because this water starts to heat up hundreds of degrees centigrade, probably over 400 degrees centigrade, it becomes buoyant and it moves up onto the sea floor. Now these chimneys, impressive as they are, don't last very long. After a while, they start to fur up on the inside and then they collapse. And they collapse to form this big mound that I'm standing on at the moment, formed almost entirely out of sulfide minerals.
With superheated water gushing up from the sea floor, these vents look like very hostile, dangerous places. Yet strangely, they are teeming with life. And until recently, we had no idea this life even existed.
At the hot springs, we find boisterous crowds of animals. It's just vibrant with life, that's why I love studying the hot springs. So what sustains them? Where does all the food come from? That's the magic of the microbes.
Cindy Lee Vandover is both a deep-sea biologist and a pilot of the deep-sea sub Alvin. She visited vent sites around the globe and found creatures making a living in a totally unexpected way. All life here depends on microbes, bacteria that get their energy from chemicals in the hot water. It's similar to the way plants use light to make food. The bacteria form the basis of a food chain that's totally independent of the sun. The black smokers of the Pacific Ocean are dominated by carpets of giant tube worms, often several feet long. These worms have no mouth or digestive system, but have a special organ packed with bacteria. The worms supply the bacteria with hydrogen sulfide from the hot vents and carbon dioxide and oxygen from the seawater. The bacteria make enough food for themselves and the worms.
They live at about 12, 15 degrees Celsius, and the warm water is rising up from the vent, and it's mixing with the cold seawater, and you can see it shimmer. They have to be in that specific area because they need to at once take up oxygen and the hydrogen sulfide, so they're very clever organisms.
The mid-ocean ridges all connect around the planet, but the communities of creatures living on the mid-Atlantic ridge are different from those in the Pacific. In the Atlantic, the black smokers are swarming with shrimp. Like the tube worms, shrimp depend on bacteria, but they don't have bacteria inside their tissues. Instead, they grow them under an inflated part of their shell over their legs. So when they want to feed, all they have to do is to reach into their armpits. Every now and then, volcanic eruptions along the ridge destroy these communities. But these same eruptions create new opportunities.
After an eruption, you establish a new hot spring. First, the tube worms come in, and then the mussels, and then the clams. There's a whole succession that happens.
Each volcanic eruption alters the plumbing of the seawater circulation. As some vents turn off, new ones open up and are quickly colonized by swarms of vent animals. But for a new colony to form, vent animals have to find a new site, somewhere along the vastness of the mid-ocean ridge. Viewing these sites without water, we see something strange happen to the hot plume emerging from the chimneys. It rises for 1,000 feet or so, and then as it cools, it spreads out into a vast disk, perhaps a mile or so across. The Earth's rotation sets this disk spinning, and it breaks away from the hot plume. The disks travel for miles through the oceans, carrying the larvae of shrimp, worms, mussels, and all the other vent creatures. Some might be lucky enough to be dropped over a newly formed field of black smokers. And some might find themselves drifting onto a very different kind of place. Further down the flanks of the mountain, away from the most active part of the volcanic ridge, are different kinds of hot springs, discovered in the year 2000. Here, the emerging water is cooler and contains different minerals, producing tall white columns, some nearly 200 feet high. This is the Lost City. Shortly after its discovery, James Cameron took 4 submersibles down here to film. He carried enough lights to illuminate the deep sea in ways not possible on research trips. These images are the nearest we get to seeing the scale and beauty of ocean landscapes without the help of computer animation. So far, we've only drained the water far enough to reveal the mid-ocean ridges. When the water level drops again, the largest landscape on the planet comes to life. Some ocean landscapes exposed by draining the ocean are so vast, it's hard to get a sense of scale. Now, we take away nearly all the water to expose the largest landscape of all. A huge flat plain. The abyssal plain. Abyssal plains cover about a third of the whole planet, about as much as all dry land combined. Off the coast of North Africa, the flat plain of mud and sand was created by a cataclysmic event. Geologist Peter Tolling walks across the aftermath of this event.
Here we are offshore from northwest Africa, and I'm standing on top of a deposit of sand and mud from a submarine flow that happened about 60,000 years ago.
That flow, an underwater sandstorm, was on a scale that's hard to imagine. In just a few hours, it moved more sediment than all the rivers in the world carry in a year. It started as a landslide through a canyon offshore from North Africa, like those in Monterey Canyon. But this avalanche was much more powerful.
And as that landslide started to disintegrate, all of the sediment in the landslide started to churn up, mix in seawater, and made its way down the canyon. The flow then came out of the canyon, and it started to spread. It spread into this abyssal plain that I'm standing in, and it spread to be over 100 miles wide.
This flow was so vast that looking down from high overhead, it's still hard to see its full size. It raced at 60 feet a second over the flat plain and traveled over 1,000 miles, eventually stopping on the flanks of the mid-Atlantic ridge. This all happened a long time ago, but similar events still happen, even though in the real world they're hidden under 2 or 3 miles of water. Pitch black and under crushing pressure, the abyssal plain is hard to explore. But each time we descend to these depths, we find something new and unexpected. These are mud volcanoes. Hot gas escaping from under the seabed liquefies the sediments, then builds them up into mud sculptures. There are mud volcanoes on land, like these in Southern California, where heap deep below ground level liquefies the mud. Mud volcanoes are not very common on dry land, but on the abyssal plain, there are more than 100,000 across the globe, and they're much bigger. These in Southern California are only a few feet in height. But beneath the Gulf of Cadiz, off southern Spain, there are mud volcanoes that have grown to enormous sizes. This field of giant mud volcanoes has only recently been mapped. And this is Al Idris, 800 feet high and 3 miles across. With the water drained from the abyssal plain, it's easy to see that El Idris is 100 times bigger than those in California. It's not just mud that oozes up onto the abyssal plain. In some places, tar emerges onto the ocean floor. As soon as it meets the cold water, the tar solidifies over large areas, like a blacktop road running across the abyssal plain. There are places on land where tar bubbles up like this. The most well-known lies in the middle of Los Angeles, the La Brea tar pits. This place is famous for animals that were trapped in the tar, died, and preserved intact. On land, this tar pit was a death trap, but underwater, it forms oases of life on the abyssal plain. Bacteria live off chemicals in the tar, like the bacteria on hydrothermal vents. Other creatures feed on these bacteria, creating rich, thriving communities. And the further we explore this vast plain, the more bizarre life we find. As well as tar, other chemicals seep up from the seabed. And everywhere this happens, life takes advantage of it. In places, the abyssal plain stretches for more than 1,000 miles, and we've only explored a tiny fraction of it. There must be many more strange creatures just waiting to be discovered. With nearly all the water drained away, our planet looks completely different. Even familiar landscapes are transformed. This is a view of the islands of the Bahamas, rising sharply vertical for more than 2 miles from the Atlantic abyssal plain. Not the usual image of this subtropical paradise. The Bahamas are a group of hundreds of islands lapped by shallow turquoise seas, often only 20 feet or so deep. These islands are scattered over an area of nearly 5,500 square miles. Poking above the surface, they're just the tips of a huge underwater structure called the Great Bahama Bank. Unlike the other landscapes we've exposed, this wasn't created by volcanoes. Instead, it was built up over many millions of years from limestone, carbonates, the shells and skeletons of countless marine animals.
We always say carbonates are not made, they're born, because really the carbonate sediment is produced by organisms.
The Great Bahamas Bank is still growing, as living creatures, from corals to tiny plankton, add to its height. The reefs of the Bahamas are just a thin living skin on a vast limestone block that's been growing for millions of years. The numbers of creatures that died over that time to create a structure like this size is almost unthinkable. We're able to see the scale of this structure without draining the water. In a view from space, The turquoise water marks the outlines of the bank, and the deep valleys carved into it are marked by deep blue water. But to see the real scale of this landscape, we need to drain the water down to the level of the abyssal plain. Now, standing on a Bahamian shore would be a totally different experience for scientist Gregor Eberle.
We're at the edge of the Great Bahama Bank on an island that is surrounded by beautiful turquoise water. If we would take that water away, we would get exposed on the platform edge to reefs and then a spectacular drop-off to 3.5 kilometers depth into the Northeast Providence Channel.
It's around 2 miles from the abyssal plain to the top of this cliff, where the waves lapped the shores, before we drained the water.
It's probably one of the steepest face on the Earth. So it's steeper than, for example, the steepest face on the Mount Everest.
The Great Bahamas Bank is not the only massive structure rising from the abyssal plain. The ocean floor is studded with underwater volcanic mountains called seamounts. Most of the volcanic activity on Earth takes place below the waves, where it produces mountains from a few thousand feet high to those tall enough to break the surface, like the islands of the Hawaiian chain. The largest concentration of seamounts is found in the Pacific, and those around Hawaii have been mapped in detail. Scientists from the Hawaiian Undersea Research Lab have dived on many of these underwater mountains and found that each was teeming with life.
Although we haven't been able to visit anywhere near the number to say for sure, it looks like from the ones that we have visited that there's an awful lot of animals that inhabit these. They're all unique and they're all different, but there's always something.
1460 meters, can we get in position?
Even more amazing is the sheer number of seamounts. Scientists have counted more than 15,000 in the Pacific Ocean alone. If each one has as much life as the few studied by the Hawaiian teams, they must account for a huge fraction of the Earth's biodiversity, most of which we don't know anything about. Not every structure rising from the ocean floor around Hawaii is a volcanic seamount. Some were created by even more powerful events. Off the north coast of the island of Oahu, there are some bizarre structures. When they were first surveyed by sonar, they were thought to be ancient seamounts, no different from the others that are scattered across the Pacific. But these structures aren't ancient seamounts. Instead, they are likely the aftermath of a spectacular explosion. These strange underwater structures off the island of Oahu have been studied in detail by John Smith. With no water, we can appreciate the scale of this landscape. The biggest block is named Tuscaloosa, and its top is about a mile below the surface. Standing on this enormous summit would be overwhelming.
I'm standing here on top of the Tuscaloosa Seamount in the middle of the Nuuanu debris avalanche field, which surrounds me on all sides. And it's actually very flat on top and very jagged slopes along the side, very steep, about a mile thick. It's about the size of the city of Atlanta.
Tuscaloosa is the biggest block, but there are many others. Some several miles across, down to others the size of houses. They're scattered over a huge area in a pattern that suggests they're not seamounts at all, but the debris from a landslide of unthinkable size. They've been renamed the Nuuanu landslide.
This Nuuanu landslide is actually one of the largest such features on Earth. It extends about 150 miles or more from the island. In fact, the debris field from the Nuuanu landslide is about the size of the state of New Hampshire.
These huge blocks might just be sections of Oahu that have gently slumped into the ocean as the island slowly crumbles and erodes. Or there's evidence that suggests they're debris from a sudden massive explosion. It's hard to imagine the scale of such an event. By comparison, this is Mount St. Helens. In the 1980s, a huge landslide triggered an explosion big enough to blow the side off the mountain. The explosion that created the Nuuanu landslide would have been much more powerful. The landslide from Mount St. Helens covers 23 square miles. The Nuuanu landslide covers 8,000 square miles. And the forces that triggered this enormous explosion are still acting on the Hawaiian Islands today. Lava streams run down the mountainside and pour into the sea, where they generate huge clouds of steam, though today's eruption is tiny compared to some in the past. Sometimes the steam pressure builds up and explodes. Imagine a far more powerful version of this to get a sense of the one that created the Nuuanu landslide. There have been many of these explosive events in this part of the ocean.
There are on the order of 20 of these large landslides, not as large as this one, but on the same order, and another 50 or so as you go up the northwestern Hawaiian chain.
Each of these landslides could have been a disaster for the island chain, as this computer model shows.
We take all the seafloor data that you've seen, and we generate a large earthquake, and as the loop plays, the effects of the waves travel up the chain, inundating some of these islands.
This animation shows that a landslide on the Big Island can create a tsunami so big that it split islands like Molokai and Maui in two. Some geologists think that the remnants of such a big tsunami could still be found on the island of Lanai.
You can see here that there's basically white and black rocks, and the black rocks are basalt boulders, the lava rocks that have been rounded and reshaped by the action at the surf zone, and the white ones are coral deposits from ancient fossil coral reefs.
Coral could have been torn from the seafloor and dumped on the beach by a powerful tsunami. These deposits go a long way inland, showing that the tsunami did swamp the island, just as the computer model showed. And maybe not just once.
We think there's at least 3 separate layers in this one section, and that they would represent different events. There's really no reason to think that there couldn't be another tsunami deposit because we've mapped out there's about 20 giant landslides just in the main Hawaiian Islands.
If this happened in the past, it can happen again. The processes that created the Hawaiian chain are still going on. Each island is still being carried away from the hotspot, the plume of volcanic activity where it was born. Once away from the hotspot, they erode and crumble, sometimes slowly and gently, sometimes in spectacular landslides. The islands are finally reclaimed by the sea and disappear below the waves. But the Hawaiian chain continues on for thousands of miles. A long line of underwater mountains that mark the slow passage of the ocean floor across the face of the planet. The journey of the ocean floor started when it was created at the mid-ocean ridges. But where does it end? Nearly all the water is now gone from the oceans. But there is still some water left. Long, thin lakes, up to thousands of miles long and hundreds of miles wide. The lakes mark the lines of deep ocean trenches. This lake covers the deepest trench of all, the Marianas Trench in the Pacific. Seafloor, created at the mid-ocean ridges, is destroyed here. It's at the end of its journey across the globe, where two of the plates of the Earth's crust collide. With the landscape drained of water, geologist Bruce Applegate stands here at a place called a subduction zone.
Subduction zones like this are characterized by oceanic crust coming down to the trench and then being stuffed under other crust. And in the case here in the Marianas where we are, the crust that is being subducted is oceanic crust underneath other oceanic crust of the Philippine Plate, which is behind us.
As the Pacific Plate sinks back into the Earth, it creates this trench, the deepest part of the ocean. Now, as we drain the remaining seawater, we reach the final stop on our journey.
Here we are in the deepest place on the planet. This particular place in the Marianas Trench is the Challenger Deep. The Challenger Deep is a little bit deeper than 11,000 meters below sea level. So to get an idea of how deep the Challenger Deep is, it's like you were standing on the surface of the Earth and looking up to the altitude of a cruising 747. So that's a lot of water.
That means that the distance between the surface and the bottom of the Challenger Deep is 7 miles. So deep that Mount Everest could sit in it and still be covered by a mile of water, over 36,000 feet below sea level.
Despite the depth of Challenger Deep, people have been here. In the early 60s, the submersible Trieste visited the bottom of the Challenger Deep.
This was the only time that people have ever been here, and the only time humans have ever been this deep. Such pioneers have visited the deepest parts of the ocean, our last frontier on planet Earth. But there will always be more to find in the vastness of the ocean basins. It's still enormously difficult to explore these landscapes.
When you're looking out of the window of a submersible, it's like looking into inky blackness. You can only see a couple of feet. So what they learned about the Challenger Deep was only what they could see very close to the submersible. But as you can see, there's a much bigger picture here.
This bigger picture is becoming clearer with every new expedition. "30 years ago, we had no idea any of these creatures shared our planet. 10 years ago, we had no idea places like this tar seep existed. Only a few years ago, we thought that the Challenger Deep was the deepest place on Earth.
The Challenger Deep is where we think the deepest spot is, but there are other deep spots not far from here.
Some of the recent sonar work that we've done have discovered other places along the trench in the Marianas that rival the Challenger Deep as the deepest place on Earth.
This is the HMRG Deep, named after the mapping team that discovered it, and may be slightly deeper than the Challenger Deep. So this is the end of our journey for now. There's so much more left to be discovered on our planet. The scale of the ocean world is unimaginable. Most of the landscapes that we've measured are vast compared to their parallels on dry land. All this spectacular scenery is hidden underwater. Yet these are the biggest features on planet Earth. Or should it be planet Ocean? Remote, deep, dangerous. We've hardly glimpsed this world. Every survey or descent reveals something new. What else is waiting, unseen, beneath the waves?